Okay, today's video, linear combinations and spanning sets. Now what I've done is I've making this video, but I've also posted a second video that has some awesome visualizations. I'm actually not sure which order you want to watch them in, so it doesn't really matter. Watch them both before you give any judgment about how well you understand all this stuff. Because it could be after watching mine, you're like, I don't really see what you're saying, and then you watch the other video and go, oh, that's what he was talking about. Or you watch that one and see the visualizations and go, I don't know what's going on here. And then when you come back to mine and I start referring to the visualizations, you'll go, oh, I remember that now. So it's probably going to take a combination of both to get the ideas here. So recall the following definition: linear combinations of vectors. A linear combination of the vectors u and v has the form au plus bv, where a and b are scalars. What we mean by that. Let me get a pen out here and write in what I mean by that. When we're talking about a linear combination of vectors, maybe we mean something like 3u plus 2v. Or maybe we mean something like 7u plus 9v. Or 14u minus 11v. Some linear combination. Now, I made all the numbers integers or whole numbers there, but there's certainly no reason that has to happen. The combinations could be decimals, fractions, whatever. That's not the point there. But the point is you're going to have some number of u's and some number of v's. And so linear combinations become very important. For now, don't worry about why they're important. Just go, okay, I can make linear combinations by going some number of u's and some number of v's. To visualize what's going on, here's an example. Two vectors, u equal 2, 1, v equals 1, negative 3. So what would 3u plus 2v look like? So it says sketch u, v, and 3u plus 2v. Well, I'm going to jump right ahead and sketch 3u plus 2v so you get what's going on here. And I'm not going to do it with all the straight line stuff. I'm going to try and draw it myself, fairly straight lines, because it goes a little faster and a little smoother. So u is 2, 1. There's u. And then it wants 3u. So 2, 1, then 2, 1 again. And then 2, 1 again. There's 3u. Then it says add to that 2 v's, and each v is 1, negative 3. So here's 1, negative 3. I'm going to do it another color here. And onto that I want to add a 1, negative 3. So there's a 1, negative 3. And there's a 1, negative 3. So there's 2v. So I've taken 3u and added to it 2v, and I had to do that tip to tail to add those vectors along. And what they want is a picture of 3u plus 2v. And when you look at that, you might go, that's what I have, 3u plus 2v. No, 3u plus 2v is the sum of those vectors. It's what you get when you add those things all up, and what you get is this thing here, and that's 3u plus 2v. And I can see in my picture, it ends right there. I made a big dot there. I know my arrow doesn't quite line up, but basically what I get is the vector 8, negative 3, which geometrically to look at, it's a nice visualization. It's not the easiest way to do these things. It's a nice way to see what's going on here, but it's not the easiest way to handle these things. And that's what's going to happen in this lesson. My video is going to show the easiest way to do these things, but not a great way to visualize it. And then when you're having trouble visualizing it, you go to the other video that I posted that I found that was really good for visualizations to help you with all the visualizations. Because if you really wanted to do 3u plus 2v, what you'd go is go, okay, 3u plus 2v equals 3 times 2, 1 plus 2 times 1, negative 3. And I get 6, 3 plus 2, negative 6, which is 8, negative 3, which is what I got over there. Isn't that way easier than having to go through and draw the whole thing? It absolutely is way easier to do it algebraically. The only problem is you can't visualize what's happening really. Okay, so we need a combination of both to be able to really picture what's happening here. So as we know from our study of geometric vectors, 3u plus 2v is a linear combination of u and v. Therefore, 8, negative 3 is a linear combination of 2, 1 and 1, negative 3. That's what that is made up of. 8, negative 3 is made up of some number of 2 1s and some number of 1, negative 3s. We know what those some numbers are. 3 of the first one and 2 of the second one. So any vector can be expressed uniquely as a linear combination of any other two, as long as they're non-zero and non-collinear. What do we mean by that? If you got two vectors and they're not, neither one of them zero, and neither one of them are collinear with the other one, then any other vector can be expressed as a combination of those two. Careful. In R2. Okay. Now, if that's not perfectly clear, well, this lesson's going to make it perfectly clear by the end, so just stay tuned. So, here's an example to show what we mean by that. Given the vectors u equal 3, 5, and v, 2, 6, express this vector 1, 2 as a combination of u and v. Apparently, the vector w equal to 1, 2 can be made up as some combination of u's and v's. What we mean is there is w, there is some way to be able to go sum a times the vector u plus sum b times the vector v. Our job is to figure out what a and b will work. It seems impossible, but the algebra is actually pretty straightforward. I mean, there's a lot of steps, but it's actually pretty straightforward what has to happen. I'm just going to sub in what we want to come up with. We want 1, 2 to be made up of a of the 3 5s and b of the 2 6s. Apparently, there's an a and b that will do this. The rest of it is just algebra. Watch. 1, 2 is equal to, I'm going to multiply that a in. I get 3a, 5a. I'm going to multiply the b in, and I get 2b, 6b. I'm going to add those vectors. 1, 2 equals 3a plus 2b. And the y component will be 5a plus 6b. I've just added those two vectors like that. And so what I end up with is two equations. That is, for the x component, that 1 is going to have to come out to whatever 3a plus 2b is. And this 2 is going to have to come out to whatever 5a plus 6b is. Now, hopefully that looks super familiar. And it's the reason this was taught in grade 10 academic math is the ability to solve for a's and b's when you have two equations with two unknowns. And there's lots of ways to handle this. I'll do it by elimination. And what I'll do is I'll label these as equation 1 and equation 2. And I'm going to multiply -3 times equation 1. And I'll show you why I'm doing that in just a second so that you will know what to do as well. And I get -3 equals -9a minus 6b. I'm not going to do anything to equation 2. Little colons here. And the reason I chose -3 is that now the b's line up. I got -6b and positive 6b, and when I add these two equations, I get -1 equals -4a. It's called elimination because I eliminated the b's. I took the b's out of the equation. What numbers should you multiply the equations by? Whatever it takes to line up an A or a B. I could have done other choices. A great choice would have been to multiply the first one by 5, which would have given me 15a, and the second one by -3, which would have given me -15a, and I could have added them and eliminated them. You can add or you can subtract. I like adding because it avoids subtracting negatives, which can cause people problems. One more step later, divide by -4, and I get the a is equal to 1/4. And then I sub a equals 1/4 into whatever equation you want, actually, whatever's going to make your life the easiest. And so you got lots of choices here. I'm going to sub it way back into equation 1. And so I get 1 equals 3 times 1/4 plus 2b. I get 1 equals 3/4 plus 2b. I get 1/4 equal 2b. 1/4 divided by 2 equals b. And I get 1/8 equals b. I hope that's not, I hope after you look over that for a couple of seconds, that those parts will be pretty good. Now, after all that algebra, it's easy to get lost on what you've come up with. But what we've done is we go all the way back to here, this line right here, and we say, therefore, W is equal to, what was my A again? My A was 1/4. 1/4 of U, and then plus B, my B was 1/8, V. Now, the numbers were weird, but there was an A and a B out there where I can make up the vector W from some combination of U's and V's. Specifically, 1 comma 2, the vector we were started off with, we called W, is equal to 1/4 of the U vector and 1/8 of the V vector. Algebraically, reasonably straightforward. And by reasonably straightforward, I don't mean the first time you see it, you go, oh yeah, that's so easy. I mean, with a few practice ones, you see they're the same every time. You line them up this way and you knock them down. It's tough to visualize what's just happened, but what's just happened is apparently, if you want to go 1 comma 2, you can do that as 1 comma 2. But you could also do it by going 1/4 of 3/5 plus 1/8 of 1/4 of 3 comma 5 and 1/8 of 2 comma 6. That will give you the same result. Shocking, shocking result. Now, back to here, what I've set up here. Any vector can be expressed as a linear combination. Where's my highlighter? In pink here, but I'll switch it over to yellow. Any vector can be expressed as a linear combination of any other two vectors, as long as they're not collinear vectors. They can't be parallel, or you won't be able to do it. But as long as these two things aren't parallel, which they weren't, U and V were not parallel, then I can make up any other vector as a combination of them. I just have to do all this algebra to solve which combination. Works in 3D as well. I'll say works in 3D usually. Okay, it always works in 2D because in 2D, all the vectors are in the same plane. So there's a big idea building here. So for now in 3D, this one says express U, V, and W as a linear express U as a linear combination of V and W. It says go ahead and do it. So it's implying it must be able to be done. It won't always work in 3D, and we got a lot to talk about in that. But for now, this question says, just do it, please. And I'm like, okay, I guess I'll try to do it and hope it works out. So, same start as the last question. What I say is U, I'm still on my highlighter there, U is equal to some number of V's, A V's, plus some number of W's. BW's. And then I just fill in the vectors they gave me. The U is 1, -1, 1. Apparently, you can do the vector 1, -1, 1 as some combination of 0, 2, 6's and 2, -3, -1's. My job, figure out what the A and B are that make this work. Again, they're telling me, because they told me to do it, that it's going to work here. I'm telling you in 3D, it doesn't have to work, and we have to investigate that more as this lesson goes on. But for now, we proceed. Let's see, 1, -1, 1. Multiply the A into the first vector. I get 0, 2A, 6A. And the second vector, I get 2B, -3B, -B. And all I've done is multiplied in the A and B into those two vectors. And then I'm going to add the two vectors together, so what I get is 1, -1, 1 equal, and the x will be 0 plus 2b, that's just 2b. The y will be 2a minus 3b, and the z will be 6a minus b. So now I've got that vector all ready to rock and roll. So this results in 3 equations this time. The x component says 1 will have to be equal to 2b. Isn't that nice? That's going to make my life easy. The y component says -1 has to be 2a minus 3b. And the third one says the z component has to come out to 1 equals 6a minus b. And you look at those equations and you make a decision. You have not run into this situation before where you had 3 equations. And you go, well, how do I solve 3 equations? Well, the same way you do with 2 equations. You just solve 2 of them. But what you have to do is check that the third one works. So, how do you solve 3 equations? Solve 2 of them and check if the third one works. That's how it will not, this linear combination thing might not work in certain examples, is the check won't check out. Apparently in this one it will. Let me finish it off to be clear. So you could do substitution or elimination on any pair of these equations, no problem. And this particular question is much easier than that. I'm just going to rearrange equation 1. and I get b equals 1/2. I didn't have to do any fancy substitution or elimination there to find that b equals 1/2. And then I'm going to sub b equals 1/2 into equation 3. And you say, well, why equation 3? Well, I could have done equation 2. Doesn't matter. I'm going to sub into one of these two equations to find out what the a is. I chose 3 because it had the simplest b coefficient, but it doesn't really matter. So I go 1 equals 6a minus 1/2. 1 plus 1/2 equals 6a. Maybe you got to brush up in your fractions a little bit. 3/2 equals 6a. And then 3/2 divided by 6 equals a. So I get 3/2 times 1/6. I get 3 over 12. I'm going to reduce that right now. A is 1/4. Maybe you need another step in there. Whatever. Okay, so I have a proposed answer here. I think at this point that b equals 1/2 and a equals 1/4 is going to work. In fact, that will work with equations 1 and 3. That's a solution to equations 1 and 3. My job to make sure this all works is to check equation 2. And I got to tell you, as soon as I finish writing this, I'm going to get the the red highlighter out to say this is an important step in all of this. Is to say, okay, I think I've got a solution here. I've got an a and b that are going to work. But I have to make sure by checking the equation I haven't used yet. So you can set this check up any way you want. I like doing it formally, a left side, right side check to make sure that these two, this a and b works in equation 2. The left side of equation 1, or equation 2 is just -1. The right side is 2a minus 3b. Let's check with my a and b. 2 times 1/4 minus 3 times 1/2. And I get 2/4 minus 3/2. I'm dragging it out here. 1/2 minus 3/2, which is -2/2, which is -1. Woo! Worked. I mean, the question predicted it was going to work. But this is where it could fail. It is possible when you have it in 3D that it won't work, that you won't be able to find a linear combination that will work. And it's because if these vectors aren't coplanar, it's not going to work. And we'll talk more about coplanar later. I'm just introducing that word right now. If these three vectors aren't in the same plane, you won't be able to find u as a combination of v and w. So anyways, they said express it as u as a linear combination of v and w. So therefore, u equals, what did I say originally? It was way back here. I set it up way back here. U equals AV plus BW. I got in this purple color, but I'm loving it here. A, which was 1/4 of the V's, plus B, which I found was 1/2. I had to look around for that, times the W. Apparently this will work. And you can check it if you want. You can punch all the numbers in and see that if you can get 1, -1, 1, if you can get that vector by going 1/4 times 0.26 plus 1/2 times 2, -3, -1. And it'll work. You'll find that works out. Okay, I've been setting up a lot of stuff here. And the basic idea is coming back to express one vector as a linear combination of another two and what that means. In R2, in 2 dimensions, it should work as long as the vectors aren't collinear. In 3 dimensions, I've warned you, it might not work. The example we did was set up to work. Okay, so a little bit more as we go along here. And I mentioned this word before, and maybe you have to go to the other visualization video now to really be able to picture this. So I'll try and explain it out loud. Coplanar vectors are vectors that lie in the same plane are said to be coplanar. More specifically, vectors are coplanar if they lie on a plane when arranged tail to tail. If you have trouble visualizing a plane, just think of the desk or the table that you're working on right now. That's a plane. And if you took a pencil or 2 pencils and dropped them onto the desk, they would lay flat on there, and those could be 2 vectors that are in the plane. They're 2 vectors that are coplanar. And the big idea is that if my third vector doesn't lie flat on the table, there's no way to make it up from the other two vectors because it doesn't stick out like those, it does stick out unlike the other two. Now that's a very basic plane to picture a table like that, but that's how I always visualize it when I'm just trying to think of what does a plane look like. Now that's a nice flat, obvious plane, but if you want to picture planes in space, think of a flat piece of cardboard and just hold it up at any angle you want. It doesn't have to be flat like the table. It can be just a plane at any angle you want. Hold it up, spin it around in space, and you'll see that represents what a plane would be. And for three vectors to be coplanar, they all have to lie in the same piece of cardboard in space. They won't always do that. In fact, there's no reason they should do that. Okay? That's what coplanar means. They all lay on the same piece of cardboard in space. Now, any two vectors will be coplanar. As soon as you have two vectors, they'll be coplanar for sure, because the plane we can just lay along the two vectors. And if two vectors in space are not collinear, they define a plane. So if you have two vectors that are lying in the same direction, you won't get a plane out of it. It won't be flattened out to get a plane. You'll just get a line. And that video shows that wonderfully, by the way. But if they are not collinear, then they will define a plane and form a basis for the plane. An important problem in geometry is to determine whether three vectors are coplanar. And I got to give it away. We just did that. Right back here in this example. It said express them as a linear combination. It worked. We were able to express them as a linear combination. That means they are coplanar. So proving something's coplanar isn't any more work than what I've done here. It's tougher conceptually. You may have to go to the visualization video, but it's not any tougher algebraically. Okay, so here's the big statement here. Get my highlighter out. If any one of the three given collinear vectors can be expressed as a linear combination of the other two, it follows that the three vectors are coplanar. Why do you think this property is true? It is true because it would not work if one vector stuck out of the plane. That's the easiest explanation I can give of that right now. But the pencils on your table example is a good one. If you drop two pencils on the table, there's two vectors that define a plane, the table. If you take another pencil and stick it straight out of the plane, there's no way to use your two original pencils to make up the third one. They have to be all in the same plane. And if they're all in the same plane, then they can be made a linear combination to make two of them to make the third one. So this question, it looks like a different question, but it's not. It says determine whether the vectors u, -1, 2, 3, v, 1, 2, 3, and w1, -2, 3. And these are simple vectors, actually, 1s and 2s and 3s, and yet virtually impossible to visualize what's happening here. The question is, are they coplanar? And when it says coplanar, you can immediately go, can I make a linear combination? If I can make a linear combination, they'll be coplanar. If I can't, it won't work. You say, well, why would it not work? That third equation check won't check out. So this is the exact same question I was just working on. It's just we don't know going in that it's going to work. So I'm going to start with saying, if they are coplanar, there will be numbers a and b so that w will be a u plus b v. There will be a way to do this. If they're coplanar, there'll be a way to make some number of u's and some number of v's, and that will make up w. My whole job, is there an a and b that will work? Very similar to the previous question I did. So w is 1, -2, 3. Let's check if it can be made up of some number of u's, -1, 2, 3's, and some number of v's, which is 1, 2, 3. The algebra, very similar to the previous question. Multiply in the a, I get negative a, 2a, and 3a. I get b, 2b, and 3b. And then I combine those vectors on the right-hand side of the equation. I say, okay, x component, oops, negative a plus b. Y component, 2a plus 2b. And z component, 3a plus 3b. And that makes up three equations. Therefore, the x component, the 1, has to come out to negative a plus b. The y component, negative 2, has to come out to 2a plus 2b. I'm just setting the x components, the y components, and the z components equal. 3 equals 3a plus 3b. And what I've got is now three equations. And I'm going to take two of them and solve those two, and then see if that a and b will work for the third one. That's what's different here about solving three equations in two unknowns instead of two equations in two unknowns. You go ahead and solve two of them and then hope it works for the third one. There's no reason it should. But if it does, we can talk about what that conclusion means. So here I go. What I want to talk about is I'm going to choose to just do 1 and 2. Me personally, I always do 1 and 2. It helps me not get confused. If I do 1 and 2 together, I'm always checking equation 3. So if you find these confusing, just solve 1 and 2 and check 3. You can do other combinations if it makes sense to you. So for 1 and 2, I'm going to look at this for just a second and go, okay, 1 and 2. Oh, I see a good way to do it. I'm going to go 2 times equation 1. And 2 times equation 1 gives 2 equals negative 2a plus 2b. I hope you see what I'm up to here. By using 2 times equation 1, I don't have to do anything to equation 2. And I've lined up the a's nicely. Equation 2 is negative 2 equals 2a plus 2b. Oh, not plus 4b. Something felt wrong there. Let me just erase that. Plus 2b. So equation 1 I multiplied by 2, yes. And equation 2 I didn't do anything to. So now I've lined those up, so now I can add. I love adding with the elimination. It eliminates some errors, and I get 0 equals 4b. B will have to be 0. To make the first two equations work, only b equals 0 will make that happen. And then I sub b equals 0 into equation 1. Yeah, I could have done equation 2, but I'll sub it into equation 1. And I get 1 equals negative a. So a equals negative 1. Now you can check that in equation 2, but it's going to work. Because equation 1 and 2 are what I was solving. That's not the concern. That a and b will work for equation 1 and 2 unless I've made an algebraic mistake. Every time you have two equations like that, this exact procedure will give you an a and b that will work for equation 1 and 2. The big question is, does it at the same time, simultaneously, solve equation 3? So I'm going to check equation 3. I'm going to do it formally with this left side, right side check. And the left side of equation 3 was just the number 3. And the right side was 3a plus 3b. 3 times my negative 1 plus 3 times 0, and I get negative 3. Does not work. So here's my conclusions. My first one does not answer the question. My second conclusion will. Therefore, W cannot be expressed as a linear combination of U and V. Why did that happen? Here's my big conclusion. Therefore, U, V, and W are not coplanar. They're not all in the same plane, so there's no way to express one as a combination of the other two because it doesn't lay on the same plane. It's sticking out of the table, if you want, where the other two vectors are in the plane. To really expand it to 3D, more think of it this way, is that you got some random piece of cardboard jutting through space, and two pencils are in the plane and one's sticking out of the plane. So there's no way to make a combination of the first two vectors that'll give the third vector that sticks out of the plane. Okay, again, go back and forth with the other video. That'll really help with the visualization of what I'm saying here. So spanning sets. And spanning sets is what we're really talking about here, so I'm not really going to say anything new here. I just got a new word for it here. Is all that's about to happen here. When a set of vectors can be used to express all other vectors in a given space, such as R2 or R3, so if you want to be able to express all the vectors in R2, we say that we need the vectors that would span that. Or R3. For example, any vector in R2 can be written as a combination of I and j. They're the perfect two vectors to use to span R2. How many vectors are needed to span R2? You need 2 vectors. I and j are a great choice because they will span R2 easily, and conceptually there's no big problem with trying to visualize that I and j can do that. But what conditions must actually be met? The 2 vectors cannot be the 0 vector. The 0 vector is no help here at all. So if you want to span R2, you can't have the 0 vector in there. Also, the vectors cannot be collinear. You've got 2 vectors going in the same direction, you're never going to be able to span a plane. They're just going to span a line. They're all going to be going along the same line. If that visualization is a problem, jump to the other video. It shows it beautifully. So that's in R2. In R3, how many vectors are needed to span R3? 3 vectors now are needed to span R3. And what conditions must be met here? Ooh, little hint that often this comes up on a test, or in this case an assignment, to talk about what conditions must be met by the 3 vectors. First of all, the 3 vectors cannot be the 0 vector. I'm not going to span anything with the 0 vector. So the 0 vector cannot be involved here. None of the vectors can be collinear. That's not going to help. And now, the big moment of this lesson, I think the third thing that must happen if they're going to span R3, the vectors must not be coplanar. If they're all coplanar, we're only going to span R2. They're only going to span a 2-dimensional space, a piece of cardboard. To be able to span all of 3D space, we need the vector to actually stick out of the plane, to not be part of that one plane. So state a set of vectors that spans R2. Well, of course, a great choice would be 1, 0 and 0, 1, commonly known as I and j. They're a great choice to span R2, but it's fairly easy to come up with a pair of vectors that span R2 that are not I and j. We could come up with 2 other vectors. So I could just make up the first vector. I could say, how about 2, 1? And, okay, what do I got to do here? I got to make sure that whatever I use here is not collinear. So I'm going to use 1, 5. And I just made that up. As long as it's not collinear, these things will span R2. And any vector in R2 I can make up as a combination of those 2 by following the procedure of the first example up there. Right there. Any 2 vectors will work, and you'll be able to express any other vector as a combination of those. In R2, when you're talking 2-dimensional, that's no problem. That'll always work. Then, set of vectors that spans R3. Well, the best set to use are 1, 0, 0, 0, 1, 0, and 0, 0, 1. Commonly known as I, j, and k. Now, stating another random set of vectors, oh boy, in 3 space, it's a lot more difficult because you got to make sure your 3 vectors aren't the 0 vector. That's an easy piece to make sure of. Not making them collinear, okay, that's not so bad. You can stare at them for a minute, make sure they're not multiples of each other, but to make sure they're not coplanar, you got to go through this whole test here. So it's not easy to come up with a set of 3 vectors that span R3, just off the top of your head. So couple of questions in 2D and then one in 3D to finish up here. It says, determine if the following sets span R2. In R2, I only have to check two things. Are either of them 0? No, neither of them are 0 here, so it's no problem. And then the question is this collinear? And if you look, negative 15 comma negative 25 is equal to negative 5 times the 3 comma 5. So yes, they are collinear. One is a scalar multiple of the other. They go in the same direction. They're parallel if you want. So no, they don't span R2. We need those two things to be not collinear before we're going to be able to span R2. If they go in just the same direction, all I'm going to get is a line out of that. I'm not going to get a whole plane out of it. The second question here, it says, do they span R2? Well, clearly neither of them are 0, so I don't have to worry about that. But the question is 3 comma 8 some multiple of 2 comma 4? Well, if the x component was going to work, that it would have to be 1.5, the k value. But for the y component to work, k would have to be 2. So no k works. No, not collinear. And what that means is yes, they do span R2 because they're not collinear. Fairly easy in R2. And this is going to seem very repetitive. The math here is the same every single time for R3, but we're just going to go through it and go through the conclusions. It says determine if the vectors u, v, and w span R3. First, are any of them 0? Clearly none of them are the 0 vector. 2, are any of them scalar multiples of each other? Are they collinear? Well, look at u and v. I look at the first component, I'd have to be multiplying by negative 3. The second component doesn't do that. I look at u and w, I'd have to be multiplying by 9, and clearly that does not work. And then v and w, I'd have to be multiplying by negative 3, and clearly that does not work. So none of them are collinear. But I could, if one pair was collinear, then I would stop right there and say, no, they don't span R3. So the only other test is, are they coplanar? And that rewinds back to, can we make a linear combination of them? So if none of that makes sense, I'm going to do that in the conclusions. Okay? For now, I'm going to go back to this test. Is there a way to go w equals AU plus BV? Let's find out if there's an A and B that'll work, and we'll worry about the conclusions at the end. W, negative 9, negative 4, 1. U, negative 1, negative 2, 1. And V, 3, negative 1, 1. So, same setup as before. Can these be made up as a linear combination of these other two vectors? And so, same steps as the previous ones, multiplying the A, multiplying the B, and then I build my three equations. The x component equation, negative 9, will have to come out to negative A. Oh, won't that be easy to solve? Oops, I didn't add those together. Sorry, another step in here. Add the x components. Oops. Plus 3b, the y components, negative 2a minus b, and the z components, a plus b. So that first one isn't that easy. Negative a plus 3b is that first equation. The y component, I get negative 4 equals negative 2a minus b. And the z component, 1 equals a plus b. So three equations in two unknowns. Solve one pair of them, and then go from there. Now, I said I always do these by solving 1 and 2 and checking 3, and that's actually true. If you just ask me to do one, that's what I would do every time to avoid mistakes. But in this particular case, I'm giving you the freedom to go ahead and look at the equations and look what makes most sense. If you look at equation 2 and 3, the negative b and the b are already all lined up. I can actually just right now go equation 2 plus equation 3. I get negative 3 equals negative a, and isn't that nice? A equals 3 just that fast. So I give you full permission to do that. Just make sure whatever combination you're checking that you use here at the start, that you check the other one, the one you didn't use. And maybe that's obvious to you, in which case, great. I'm going to sub A equals 3 into equation 3. and I get 1 equals 3 plus b. I get negative 2 equals b. So now I've got an a and b that will work for equations 2 and 3. I did all my work in equation 2 and 3. You can check those right now, but the procedure's right. That will work for 2 and 3. So what I really have to do is check equation 1 to see if this a and b will work back in equation 1. And I'm going to do it really formal, like with the left side, right side, check in equation 1. Equation 1 had negative 9 on the left side. It had negative a plus 3b on the right side. So it's negative 3 plus 3 times negative 2. Put all this together, I get negative 9. Okay, it checked out. Now slow down for just a second. And there's a bunch of conclusions here, and only one answers the question. First conclusion, therefore, W can be written as a combination, a linear combination, but as a linear combination of U and V. So that's the first conclusion. Doesn't answer the question yet. W can be written as a linear combination of U and V. Therefore, U, V, and W are coplanar. If they can be written as a linear combination, then they are coplanar. And now my final conclusion, which answers the questions, therefore U, V, and W do not span R3. So it's a good news, bad news type thing here. We have found out that they are coplanar. Woohoo! That's great news, isn't it? I don't know, it depends on the question. Yes, coplanar, but that means no, doesn't span R3. They're all lying in the same plane, and that's not going to span three-dimensional space. All right, folks, I encourage you to now go back and watch the other video. Maybe again, maybe you watched in the other order, but now some of that visualization will make sense. You're going to have to go back and forth between them. Maybe you're going to have to do a few homework questions, then come back and watch one of the videos. But all the information's there on those two videos. And it's a tough part of the chapter, but I got to tell you, this kind of stuff is where we're going with all this vector stuff. Up till now in vectors, you might have been like, oh, vectors, so easy. This is so nice. Yeah, things are about to heat up. So don't leave this lesson behind without doing a lot of watching of the videos to be clear on what's happening here, because we're going to use a lot more of this later. This is the last section of the chapter. From here, we move on to evaluation of the chapter. So check out the website to see what comes next there. Have a great